So last week, we discussed lots of Hamiltonian mechanics, and in particular, we discussed these very advanced topics of integrability and hidden symmetries and stuff like that. So the last topic I would like to discuss regarding the Hamiltonian mechanics is the constraints. I will only briefly touch on this, and I'll assume that most of it you have already seen, but I think it's useful to discuss it. And we will also have a tutorial today on constraints. So imagine that you have a situation where not all Qi, the generalized coordinates and the generalized momenta, are independent. And that means that at any instant of time, we have a constraint. Any instant of time, we have a constraint. And you can always arrange things so that you write your constraint is that some function of Qi and Pi is equal to 0. So what I will typically be doing, however, is that I'll distinguish two cases. And in the first case, which you've probably already seen, it's even more special. In that case, you have just phi as a function of Qi is a function is 0. And so an example of that is a pendulum where you have x squared plus y squared equals to L squared. So by the way, I require that this is true for any instant of time. In other words, for all times, we have this constraint. In other words, d phi over dt equals to 0. So phi is a conserved quantity. So this is a conserved quantity because this is true in any instant of time. And we know that there exists the corresponding symmetry, right? So we know that this generates some flow in the free space, and this flow will be a symmetry of your Hamiltonian. So there is a corresponding symmetry of physical system. All right, so this is basically the general thing. So if you have a constraint, that means you can sort of treat it as having a symmetry. And if I have a symmetry, I also have the corresponding symmetry if I have conserved quantity. So now the standard example is the pendulum. Standard example is a pendulum. And so you can either describe this pendulum, which is this thing here, in a clever way. That means that you parameterize your swing of the pendulum, just going like that, just by the angle phi. So I would say that's the Occam description. So Occam was a guy who was saying, like, you shouldn't make things more complicated than they are, so just always describe them as simple as possible. So we know that this is a system with 1 degree of freedom, and I can choose this to be phi. So why should I be describing it in a more complicated way as a system of 2 degrees of freedom? But we shall see that description also has some advantages. But anyway, so this is the Occam's description. I have 1 degree of freedom. So n equals to 1, which is the degree of freedom I have here. And of course, the phase space is just two-dimensional. So we have phi and p phi, and there is no constraint. And this is what typically the Lagrangian mechanics is good for, is that you always choose your generalized coordinates in such a clever way that you don't get the constraints, right? And typically this is quite good. However, you can describe the same thing from this other point of view, which is as a constraint description. Constraint description. So really, I now use my coordinates x and y. So I think this is x, this is the coordinate y. I have 0, 0 here. And so now I'm pretending that this is a system with 2 degrees of freedom. So n equals to 2 degrees of freedom. Of course, now my phase space is twice as big, so it actually it's 4-dimensional. So phase space as x, px, y, and py. But we have also a constraint, so I didn't say it here, but we assume that the length of the pendulum is fixed and it's equal to L. So this is L. So we have a constraint x squared plus y squared equals to L squared. Okay, and that's our constraint. So of course I can freely go from this system to that system by just doing the right coordinate transformation. I can just say imposing the constraint, so I can satisfy the constraint if I set x equal to L times cosine phi and y equals to L times phi. So then this constraint is automatically satisfied. And then, because L is fixed, I return back to this. So you can eliminate the constraint. By setting x equals to L times cosine phi and y equals to L times sine phi. And then I go from that description to this description here.
I think it should be the other way around. Because you define phi as a...
Okay, so I define phi here.
Yeah.
So it should be sine. Thank you. Sine phi and then cosine phi. Thank you so much. All right, so I can go back to this description here if I use this coordinate transformation. However, it's not always useful to do this. And the reason is that if you don't do it, so advantage of more complicated description is there's basically two. So first one is I have an extra symmetry now, right? So I have an extra symmetry. All right, so it may not be obvious, but I have this constraint. So I have this concept quantity. So I have complicated system with 2 degrees of freedom, but I have a constraint, I have a symmetry, I have a concept quantity. Meaning I have the corresponding flow, which is the symmetry of the system. Right? So here, this is not really a big advantage, but typical things what people do is that, for example, they start with Einstein's gravity, which has just the diffeomorphism invariance. You can change the coordinates, and then they actually make it more complicated, and they go to the wild gravity, where they sort of add a scalar field to the system, and then they have gravity plus scalar field. So now they are adding a degree of freedom. However, at the expense that they actually now have a conformal symmetry in addition to other symmetries. Okay, so you are making your system more complicated by adding some degrees of freedom, but you are getting some nice symmetries. And that's sometimes really, really good. And so here we have this nice symmetry of that always x squared plus y squared is equal to r squared. Okay. Second thing which people typically use is that maybe you are interested in how much actually the string is pulling your mass here. Right? So what is the tension of the string? And you can typically calculate it, and so that's called constraint forces. Constraint forces. And you can calculate them using this more complicated description here. So if you want to calculate, for example, the string tension. Okay, so really there is something good about constraint description, and although you are making your system apparently more complicated by adding some degrees of freedom, you get an extra symmetry, and you can learn more about the system. Okay, so now this is what it is. Are there any questions? All right, so now I'll just give you the prescription. I'm not going to derive it, although the derivation is probably something like 3 lines, but I'll just refer you to some mathematical books. So to deal with symmetries, yes, symmetries, use the method of Lagrange multipliers. So if we have M symmetries, so let's say you have phi j, which is j is 1 to M symmetries, then what you are supposed to do is that actually if you want to find the motion, you don't just consider the Hamiltonian as given to you, but you have to add these constraints. And so instead of H, consider now the total Hamiltonian. Total Hamiltonian, and it's given by whatever your original H without symmetries would be, plus you sum over all these constraints, sum over j, and then lambda j, t, and then phi j. So this is your original Hamiltonian, this is your total Hamiltonian, and the statement is you should be varying with respect to this total Hamiltonian, and what the correction is that you sum over all possible constraints you have, and you multiply these constraints by these things which are called precisely the Lagrange multipliers. Lagrange multipliers. And they are arbitrary functions of time. Arbitrary. Functions of time. And that's it. So that's the prescription. What you have to do is that really, if I want to solve a system with symmetries, and this is my Hamiltonian now, and now I write down the canonical equations with respect to this new Hamiltonian. So who hasn't seen Lagrange multipliers? Everybody has. So that's perfect. So now, interestingly, this is everybody agrees on, so this is what you should really do. But then what you do next, actually you have two possibilities typically. So one possibility, which you've probably done in your mechanical courses, is to say, well, I actually, this looks like a new generalized coordinate, lambda, right? So I extend my phase space by including lambda j, generalized coordinates, and of course the corresponding momenta as well. And then I vary the action with respect to the old coordinates q, but also with respect to these new lambdas. And then you get lots of Euler-Lagrange equations, some of which will be precisely the constraints. So you can actually derive your constraints as Euler-Lagrange equations or Hamilton-canonical equations. Okay, so here I am doing Hamiltonian description to confuse you. Now I will switch to Lagrangian description. So we have two possibilities. And I'm sure you have seen the first one. So possibility number one, possibility one is to enlarge space by including lambda j. So now I have also these to be my generalized coordinates, the Lagrange multipliers. So now, if my original system had n degrees of freedom, and I am adding m constraints, meaning m Lagrange multipliers, now my phase space, my degree of freedom is just n plus m, or the phase space is twice as much. But now you vary the resulting action with respect to all these things, so you get also n plus m Euler-Lagrange equations, and that get n plus m Euler-Lagrange equations, because I treat these as just the normal coordinates. All right. So as I said, to confuse you, here I described in terms of the Hamiltonian. Let's describe in terms of the Lagrangian now. So the same thing is Lagrange multipliers works at the Lagrangian level, if possible. Then you have the old one, but now you have minus lambda j phi j. And the minus comes from the fact that basically this term is something like the potential. So typically the Lagrangian is kinetic energy minus the potential energy. But the Hamiltonian is kinetic energy plus the potential energy, and so there's this difference in signs. Okay. So now if I vary the action, then I have dl, but I have also minus lambda j delta phi j, and then minus phi j delta lambda j. dt, and then you integrate by parts as you would typically, but the only thing which you need to integrate by parts is contained here. So you just get the same Euler-Lagrange equations from L as you would, but then you have this term in addition to that. And so this approach is typically used in the fact in the case when your constraints depend only on the coordinates. They don't depend on the velocities as well. So here I'm just treating the case here phi j just function of the coordinates, not of the velocities. So then you just rewrite this, and it's easy to convince you that this will be the case. You just take the total Lagrangian dqi minus d over dt dl total dqi dot. This is, of course, doesn't do anything with the constraints because it doesn't depend on q dot, delta qi, and then minus phi j delta lambda j dt. And then I have one more bracket here, probably. All right, and so you want to set this equal to 0. So it's obvious that you are getting the Euler-Lagrange equations, which are just the standard Euler-Lagrange equation, but now with respect to the total Lagrangian. And then, of course, this is a variation which is independent to that one because this is a new coordinate. So this is also has to be equal to 0. So the corresponding Euler-Lagrange equations are just dLt dqi minus d over dt dLt over dqi dot equals to 0, and then phi j equals to 0. So you have n plus m Euler-Lagrange equations, which you can, of course, solve. Yes?
Could you explain again why you got rid of the variation of phi?
I didn't. So I'm making the assumption that phi now depends only on q, so it doesn't depend on q dot. That's first thing. So then, if you look at what this guy is, it's just the old L over dqi minus lambda j d phi over dqi.
Yeah.
So which is this term here, right? And then this thing is not adding anything else because I'm not letting phi depend on q dot. So you can write it this way. So I'm just rewriting whatever the equality is. But now I just want to stress that all you have to do is just write down the Euler-Lagrange equations, but not with respect to the old L, but with respect to the total L, which contains the constraints. But you're also getting the constraints as your Euler-Lagrange equation. Okay? So constraints are recovered as Euler-Lagrange equations. You have n plus m Euler-Lagrange equations, so we can solve for everything, right? So can solve for everything, meaning qi, but also lambda j, because I simply have that enough equations. And the statement is you can also calculate the constraint forces. So what is a constraint force? Calculate constraint forces. So now what you do is that you again break this nice formula into L and the constraint part. So you can write down this formula as d over dt dl over dq dot. Okay, so there's no more contribution because phi doesn't depend on q dot, and that equals to dl over dqi, but also there's this other term which is lambda j minus lambda j d phi over dqi. Okay, so this is how I'm breaking now this Euler-Lagrange equation more closer to the first line in the variation of the action. So now this would be your typical Euler-Lagrange equation, but now we are getting, in addition to this thing here, and this is precisely this time what is called the constraint force. So this thing is the constraint force. And if you look at this thing here, so phi is a constraint. It's a surface in your phase space. So phi equal to 0 is a surface in your phase space. But what you are considering here is a gradient of phi. Right? So now I do gradient of phi. Of course, that's something which is perpendicular to your constraint surface. So constraint force, something which is perpendicular to constraint surface. And so in our case of the pendulum, of course, the constraint surface it doesn't matter which picture. So the constraint surface is simply that R equals to R equals to L. So this is my constraint surface. I always stay on the surface, and then the constraint force is perpendicular to that. I don't know which sign. It's either that or that. And so it's precisely either the pool of the string, or it's actually, how much the mass. Yeah, it's either the tension of the string or the pool of the string. So this is how you calculate the constraint forces, and you see that because I can solve for lambda j, and I can solve for q, I can solve for this constraint force. And so really, if you are interested in the tension of the string, you can solve it from here. You will do it in your tutorial today. Are there any questions to this first approach? Yes.
Does the Lagrangian formulation still work if it's a hidden symmetry?
You mean I will be a hidden symmetry, which will be my constraint? Yeah, Lagrangian formulation. If you want. You can still write down that phi, but certainly doesn't fall into this category of. So your phi now would depend on q dot, right? So this is not what I'm precisely discussing here. So I will be careful there. So now second possibility. So possibility number 2. It's really confusing. And so basically you say, well, I don't care about lambda j's, right? So I still do introduce the Lagrangian T or the Hamiltonian T. I still do this, or I still do that, but I don't really want to solve for lambdas. Let's keep them arbitrary, okay? So let's keep lambda j, which are a function of time, arbitrary. So I'm not enlarging my phase space. I just keep whatever the description in terms of qi is, and I don't include these lambda j's into that, and treat them as arbitrary functions. So now, of course, in that case, we just have n Euler-Lagrange equations for qi, right? But these n Euler-Lagrange equations for qi, they also contain these arbitrary functions. They contain m arbitrary functions lambda j. Okay. So surprise, the solution qi will depend on these arbitrary functions lambda j, right? And so, if I consider my initial value problem or whatever, so I start at q0 and p0, and then I choose one set of lambda j, okay, and I write down the solution, and this is what I get. So this is for some choice of lambda. Let's say I choose lambda j to be 1, 2, 3, whatever. And I get over here. But nobody told me that I have to choose really that set of lambda j's. I can choose a different set of lambda j's. So then I choose another lambda j, lambda prime set. And I end up in a different point in the phase space. Or you can choose another lambda, and you end up here. Okay. So now it seems that you don't actually have any predictability because your solution simply contains these arbitrary functions, and I can get anywhere I want in the phase space, right? Well, not entirely anywhere I want, but there must exist some choice of lambda so that I get here. There must exist some choice of lambda so that I get here. And there exists some choice of lambda so that I get there. right? But remember, we have these extra symmetries now. So the symmetries are the constraints, right? And so the statement is that although it seems that I have very non-unique description, so is it non-unique? Non-unique. So did I actually lose a notion of time evolution? And the statement is not really, because all these things actually must be connected by the symmetry of the constraint. Connected by symmetry of constraints. Okay, so really, the physics is still unique, right? So I really get some real-time evolution, but because I've chosen a description which is apparently non-unique, my solution depends on arbitrary functions, lambda j. It seems like I have lost the predictability, but it's not so, because all these things are actually equivalent. And they are simply connected by this flow of the constraint. So we get, it's called equivalence class. Of solutions. And the endpoint configurations are connected by the symmetry of the system. And so this description may seem strange to you, but it's actually, quite useful, because again, you have this extra symmetry which you can exploit later on, and you can sort of fix the gauge and then say, well, this is actually the right evolution or whatever. So now, interestingly, as you will discuss in your tutorial, predictions, of course, are still possible. Predictions are still possible. But you have to be asking the right kind of questions, and these questions are called relational questions. Relative questions. We are approaching fast special relativity, so you'll have like relative questions. And so what they are, you will study today in your tutorial. So if nothing is clear at this point, that's fine. You will have very concrete example where everything will become very, very clear. Okay, so the example which we will discuss will be a toy model of a theory where you consider a motion of free particle using lousy clock. So in other words, instead of having tuned your clock to the nice inertial time of Newton, you will be using a clock with which you swam in the sea and water got in. And so since then, the clock is actually running crazy. Right? It's speeding up and then slowing down and whatever, stopping for, well, probably not stopping. That wouldn't work. But you'll be using lousy clock to describe just free particle motion. And you will see that if you actually do that, and let's say starting from the Lagrangian description, go to the Hamiltonian one, you will find that the true Hamiltonian is equal to 0. Okay, that's obvious, right? I completely screwed up the time evolution. That means that there cannot be any Hamiltonian which describes this, right? Because the time evolution is completely arbitrary because of my lousy clock. So the true Hamiltonian will be equal to 0, but you will find a constraint. You will find a constraint. Find this one. So then there will be the total Hamiltonian will be non-trivial, right? It will be just h plus lambda times phi. And that's the only evolution you have in your so you have ht, which is h plus lambda times phi. And so this defines some kind of evolution. Some kind of evolution. Of course, it's the flow. Because the flow with respect to the Hamiltonian is 0, then the evolution of this thing will be the flow with respect to the constraint. Right? So then the question is, what does it mean? And can you make sense of, can you make any predictions where the particle will be at this time, where the particle will be at that time, and so on. So can we make predictions, and can we agree on them? And can we agree on them? So in other words, let's say I am using my screwed up clock and my friend is using another screwed up clock, which is completely screwed up in a different way than mine. Okay? So then can we ever agree that the particle at some time was here and that the particle at some time was there? In other words, I am using one set of these lambdas and my friend is using another set of these lambdas and he gets a different answer. So can we ever agree on something? Right? Can we ever agree where the particle actually was in the phase space? And you will study this in your tutorial. So look forward to it. Start thinking about it if you want. Okay, so I already spent more time on constraints than I wanted. So the last thing I wanted to say about constraints is that how these constraints may arise. And there is a beautiful book by Dirac who tells you everything about constraints. But in our case, let's say we start with the Lagrangian description. So returning back to the toy model, we start with L. And then we want to proceed and study the problem in the Hamiltonian description. Okay, so typical origin of some constraints. Is the Legendre transformation, Legendre transform from L to H. So if you're going from the Lagrangian description to the Hamiltonian one, and so the tricky part is not when you write actually H to be PQ dot minus L, but the tricky part is when you define what P means. So remember, you had to define P to be dl over the qi dot pi. So this is your thing. And then in order to write down the Hamiltonian, this must be invertible. Must be invertible. Meaning I have to be able to write qi dot as a function of pi and q and t. Right? So this I have to be able to, because then I'm plugging whatever the q dot in the Lagrangian was, I have to express it in terms of q and p. Right? So this I have to do. But the statement is this need not to actually be the case. And so this may not happen, so we may not have an inversion. And this happens when, so if you define a matrix, Ij, Aij, d square L over the qi dot, the qj dot. So just form a matrix like this. And the statement is, if degenerate, then this is not invertible. Not invertible. Okay. So how you really proceed is that you calculate this matrix here, and you find a matrix. And how do you find that the matrix is degenerate, for example? Determinant, for example. So if If you calculate the determinant of this matrix, you find that it equals to 0, then the matrix is degenerate, and then you know that you are in trouble going from L to H. In fact, what you can show is that if you look at the eigenvalues of this matrix, so how many 0 eigenvalues you find, that many constraints will arise going from L to H. So number of 0 eigenvalues gives the number of constraints and the number of Lagrange multipliers and so on, right? So you can verify this again in your example today. So this is typically the origin of constraints going from one description to another description. Of course, this is a problem if you want to quantize fields, right? So how you quantize fields, for example, well, scale field is simple. You either do it in the Lagrangian covariant way, then you use the path integral, or people perhaps like more the Hamiltonian quantization, where you define what Q and P is, and then you promote the pass on brackets to commutators. You promote Q to Q hat and P to P hat, and you impose the commutation relations, and this is how you quantize, right? And you will do it in a month or so in QFT1. So the Hamiltonian quantization is the simplest one, typically. But the problem is, and this works very well if you want to quantize scale field, but if you want to quantize electromagnetism, and you want to go from Lagrangian description to the Hamiltonian one, you precisely find this. You find that actually some of the momenta are actually screwed up, and you find that there are constraints in the system, and then you have to deal with these constraints if you quantize them. So this is precisely, so this possibility number 2 is really coined for what happens if you want to quantize gauge theories and stuff like that. Okay. All right, questions? So today you will study the gauge theory of free particle using the lousy clock. And then you should be thinking about this when you quantize the electromagnetic field later on in QFT1. All right. So as I said, I expect you to be a little bit confused here at this point, but hopefully the tutorial will clarify all these things. So now what I would like to do is I would like to start the chapter number 3, which is the classical field theory. So I will skip the number mechanics. For you, it's too good just to know that there is something like number mechanics. It's a generalization of Hamiltonian mechanics in case the motion would not be described by simply one Hamiltonian, but you would need more. You would need more functions to describe the dynamics. It's possible mathematically. There's a beautiful theory behind it, but there is no examples in nature at this point where you would need that. So that's why the number mechanics actually didn't really take off. Right. So part 3 is the classical field theory. And part A here will be vibrations of string. And so I'll just use this to introduce what I mean by field and to show how typically people think about fields. So it's like a transition from discrete to continuum. So field is something which is defined everywhere in space and time, and it's a continuous quantity. But of course, the question is whether this is really the true description of nature, or whether that's only a convenient description of the nature. So now if you want to describe whatever the theory of quantum gravity, and you treat the space-time as continuous, you of course run, and in QFT as well, you run into troubles, right? And so then what people do is that actually they discretize space-time, and they say actually it's not continuous, but there's some finite amounts of space, and I cannot go to a volume smaller than something or whatever, and then you are basically getting back to a discrete system. So anyway, so originally people went from discrete systems to continuous systems. Now I think people are getting back from continuous to discrete systems. Anyway, so what we want to do is, let me divide this blackboard onto two parts. In this part, there will be a discrete system. And on this part, there will be a continuous system. And I want to describe a vibration of a string, so I have a picture in mind that is my x direction, that is my displacement of the string. And so if I take a picture of the string at some instant of time, I get a picture like this. And then this string will vibrate in this transverse direction here. So the string is from 0 to 8 to A, and then on the string I have some beats, and they are completely identical. So I have n beats, and they are separated by distance L in the x direction, meaning that this is my distance L, and the string only vibrates in this direction, so this distance L is not changing. So it vibrates like that. It's a transverse vibration of a string. And then I'll label these beats by the position. So let's say this is the beat number j. So this is the displacement of that beat qj at time t. And this is a displacement qj plus 1 at times t, and qj plus 2, and so on, up to n. So label beats by position, and then qj of t is the displacement. Of jth beat. All right. So now you want to describe the mechanics of the system. So by the way, each of the beats has also its own mass, and they are all equal masses. They are the same identical beats. So each of them has mass m. Okay. So now you want to describe the mechanics of the system, and so you want to write down what the kinetic energy is and what the potential energy of the system is. So by the way, there's many ways how to introduce fields. Of course, the nicest one probably is when you study the vibrations of atoms in the lattice, and then you do the continuum limit. But this is actually a little bit simpler, so I chose on this one here. So anyway, so we are still here on the discrete part of the system. And so you want to write down the kinetic energy, T kinetic. And of course, I just have all these beads. They have the same mass, and so as they vibrate, they have some velocities which are just qj dot. So the total energy is just 1/2 sum over j1 to n, and then m qj dot square. That's my kinetic energy. I just sum over all possible beads, and that's my kinetic energy. Now the potential energy, okay, I'll introduce the tension of the string T, which will be a constant, and then the statement is the potential energy is simply T times delta Lj. So what I mean by delta Lj? So originally So I'm assuming this is a constant, that's a tension of the string. And this is not really changing during time. It's supposed to be a constant. And so this is linear in the displacement, so it's a harmonic force. And what I mean by this delta L is that, let's say, this is my jth beat, and this is my beat j plus 1. Then the original distance between them were L. But now this distance actually got increased. Now the distance between them is this one here. Okay, so this is L plus delta L. So what is the distance now? So this is distance now. It's this thing here. I'm rediscretizing thing and treating that they are really closely separated in L. And so this delta L, which is the difference between this distance minus that distance, is simply from this triangle is just L squared plus qj plus 1, which is this value here, minus qj square, qj square root, which is this distance minus the distance L. So now what you do is that you take L out and treat this thing over L as small quantity, and do the Taylor expansion into the first approximation. So what you are getting is that this is L times 1 plus this thing over L square root, so there'll be 1/2 of this thing here. And then L cancels L, and to the first approximation, we just get this is 1/2 L qj plus 1 minus qj divided by L squared. Everybody happy with this Taylor expansion? And this is what I would call delta Lj. Okay, so all you have to do is now to plug it back. And so you are getting that this is, the potential energy is just given by 1/2 sum over J L, and then T qj plus 1 minus qj square divided by L square. The Lagrangian is just T kinetic minus the potential energy, and it's just this minus that. Everybody happy so far? Excellent. So this is the discrete system where I treat that the beats are very close by, and then actually these things are not that huge. So I'm treating this thing much smaller than that thing. So the vibrations are really teeny tiny. So that I can use this Taylor expansion here, and then this is the answer. So now what you do is that you return back to this picture here, and you say, well, actually, what I'll be doing is that I will put many more and more beats. So suddenly I'll do a limit n. The number of beats goes to infinity, but at the same time, I'll make a distance between them much smaller. So I'll be really doing this thing, putting lots of beats, and making them closer and closer. So the limit which you want to do is the limit n goes to infinity, L goes to 0. And so what you should get. And now instead of q of t, I will call it psi of t. This is my x. And so I'll have now the same displacement here. but now I can just label the position of this thing to be x, not xj. And then the displacement here will be psi at that position x of t. And then I'll have another one, psi x prime at t will be this thing here, and so on. And so the next one will be the distance dx away. And that will be x plus dx of t and so on. Okay, so now, of course, so this psi x of t, this is the label where I am, which is what previously was this label j, right? So previously I had the label j, I said this is my jth beat, this is j plus 1. So now I'm saying this is my x beat, and x plus dx1, right? So I'm just making this continuous limit where I am. But of course I can write it, so this is telling me where I am on that, and this is telling me when I am on the string. But I can, so these are both labels, right? So this is the label of time, and this is the label of space. So they're exactly the same labels, so why don't I write psi x of t? And suddenly a field emerged. Okay, so psi x of t is the field. Which describes my deformation of the string infinitesimally, continuously. And so if you want a definition of field, at this point, it's just a physical quantity. Or entity, well, let's put even, this is better. My notes are better. Physical entity, something which is really, really, physical and real. Physical entity that depends on space and time. So see that in my stupid notations, these Q, so we have a mechanical system here. So we are interested in the positions as a function of time. But now, the positions we call the field, right? So the position is psi, and the position in space is just a label which labels that field. Okay, so that's the difference. Anyway, so we have now the field. And so how do you do the limit of these quantities? So again, you want to write down the Lagrangian for this thing. So let's start with this here. So T kinetic of this. So before we had each beat was of the mass m. So now I have continuous beats. So the mass m is simply the mass density times how long that piece of the string is. Okay, so basically what I'm doing is I'm saying m, something like mu dx, or the length of this thing here. Okay, so very good. So using that formula there, it's 1/2 sum over j, 1 to n, and then, sorry, mu L. That was the mass. So mu L mu, and then Qj dot. Well, Qj is just psi x, so it's just psi x t dot. Psi dot square. All right, so this is what it is. And now we want to take the limit. L goes to 0 and n goes to infinity. So we are taking now the limit. N goes to infinity, L goes to 0. And so this guy goes to 0, but this sum goes to infinity. So it's not that surprising that the sum becomes an integral over dx. Okay, so this just goes to 1/2 integral dx mu psi dot square is a function of x on t. And dot I still mean the derivative with respect to time. Okay, so that's your kinetic energy. Now your potential energy, again, is the limit n goes to infinity, L goes to 0 of this thing here. That's 1/2 sum L T Qj minus Q, well, psi x minus psi x plus dx over dx or whatever square. So what this is really written here is the derivative of psi with respect to the x direction, right? So this is I'm going in that direction, dividing by that distance. So this is really the derivative of x.
Wasn't that an approximation? That L was big.
And that approximation, yeah. So here is an approximation, but here it becomes exact because the limit L goes to 0 to this thing is just exactly the definition of the derivative. So what's really written here is psi, well, and then d psi over dx x square. And this is again the integral. So you are getting that this is equal to 1/2. Now we're just messing the notation. I'm sorry for that. Integral dx t and then psi x square. All right. So we have the Lagrangian here, which is just t minus v. So L is just t kinetic minus v, and that's equal to 1/2 integral over dx, and then you have mu psi dot square minus t psi x square. Okay, and that's your Lagrangian. Yes?
So you said, so this approximation on the left, we're basically doing a small angle approximation, right?
Yeah.
Saying the change in Q is small compared to the change in L.
Yeah.
Did you say that becomes exact now, or do we still require that the angle of the string is always fairly small?
Well, I'm saying if I make this smaller and smaller, the approximation will become more and more exact, right? Because so I'm doing several approximations, right? The real string is doing something like this, right? Going there, and so now I'm approximating by a straight line. So that certainly will be better if I make L smaller and smaller. This certainly will be a derivative. Yeah.
The ratio between delta Q and delta Q and L won't necessarily go to 0.
Where small. So I think I'm still using the approximation of small vibrations.
Okay.
All right. So we have this result here. And now look at the beauty. So if you want to study the action, so now we just concentrate on the continuous case. And we look at the action. And action is the integral of L dt, but L itself is an integral of something over dx. So in fact, we have an integral over dt and dx of something. And that something has its own name, and it's called Lagrangian density. So your action, which is an integral t1 to t2 L dt, is simply an integral from t1 to t2 dt, but also an integral from 0 to a of dx of this thing here, which is 1/2 mu psi dot square minus t psi x square this thing. And of course, so you always write it as an integral over dt and dx. And this you call the Lagrangian density. And in principle, it depends on psi, psi dot, psi x, and t and x. Right? So before it depended on q and q dot and t, but now we replace q with psi. But psi is function of both t and x, so it can depend on the derivative with respect to time direction, on the derivative with respect to the x direction, and t and x are your labels now. So this is called the Lagrangian density. So whenever you have fields, you simply just replace the Lagrangian with the Lagrangian density, and you integrate instead of over t only, you integrate over t and space. Well, very good. So we just write this as an integral dt dx of L. So now you impose the variational principle as you did for mechanics. So still the variational or action principle requires that delta S is equal to 0. Okay, so let's write what it is. So first, schematically, so in the same way as we did with Q, we just partially differentiated with respect to Q and then put delta Q or whatever, delta Q dot. So in the same way we do it here. So it's an integral over dt, integral over dx, and then you have dl over delta psi plus dl over d psi dot delta psi dot plus dl over d psi x derivative delta psi x derivative. And that's it. So remember, in the same way as we treated, we didn't touch time when we were deriving the Euler-Lagrange equations. We don't touch t and x. So these variations, they commute with the derivatives with respect to t and derivatives with respect to x. Okay. So let's do it concretely for our Lagrangian density. So the Lagrangian density is given by this 1/2 mu is the mass density, is a constant, psi dot square minus t is a constant, the tension of the string psi x square, so it doesn't depend on psi explicitly, right? So this thing is 0. So when we were going from Lagrangian to Hamiltonian mechanics, we had dl over dq dot, and we call it p. So we have the same thing here. We have dl over the psi dot, so let's call it pt. P. Well, of course, concretely what it is, if I differentiate this thing over psi dot partially, well, I get twice, so it's mu psi dot. Mu psi dot. Similarly, now we have the derivative in the x direction, so let's call it px. And you differentiate this thing, it's just minus t psi x. Everybody happy so far? All right. So now what you do is that you integrate by parts as you did before. So you want to move this time derivative from the delta psi onto this. So you are integrating over time. You're doing integration by parts in the time direction. And the same thing here. You want to move the x derivative from this delta psi x into this term, but then you are integrating over the x direction, right? So you are doing different things here. So what you do, what you get in the end is after the integration, so t1 to t2, 0 to a, and so dx, then you just shifted the derivative from psi dot into pt. So you have pt dot, and then pxx delta psi. So that's after you integrate it by parts. And then you pick up the boundary terms. But in one case, the boundary term is over t, and in the other case, the boundary term is over x. So 0 to a, pt delta psi, t1 and t2, and then plus t1, t2, dx delta psi, 0 to a, dt. Dx hiding here. Okay, so this is the boundary term which I got from integrating the time direction. So that's why I have these limits are in the time direction. But of course, the x integral still remains. And this is the integral which I got by integrating the x direction. But of course, the time integral still remains. All right. And so we want this to be equal to 0. That's our action principle, right? That's how we find the motion. Well, we have 3 terms. So the first term, it just tells you about the variations in between T1 and T2 and between the endpoints, 0 and a. So really, you are describing the motion of what happens inside a string, right, at any time t. And so the variation here is completely unconstrained, and that's why you have to have this thing equal to 0. That's your Euler-Lagrange equation. So we have that p dot plus pxx have to be equal to 0. If I just use this thing here, so pt is just psi dot, so dot is psi double dot, and pxx is just psi xx, right? So what you are getting from here is that psi xx minus 1 over v squared psi double dot equals to 0, where v is just t over mu. So you are getting a wave equation with some velocity given by the tension of the string and the mass density of the string. Okay, so you are getting the wave equation, whatever you would expect. The vibrations of the string are waves, so they should be described by the wave equation. Okay, I'm just plugging in what pt is and what px is. So that's good. So we have a wave equation. So now what about this term here? So this term tells me about how things look like at T1 and how they look like at T2. So remember, when we were considering just the mechanical problem, we said at T1 we have the fixed q here, delta q is 0, and at T2 we have the fixed q here, delta q is 0. So what this thing really describes is how the string look like at T1 and how the string look like at T2. That's our initial fixed end conditions, right? So this is just a fixed end condition and condition, which now actually tells me the initial data. So how delta psi at T1, delta psi at T2 is equal to 0. So I specify how the string looks like at T1. And I start evolving. And then I specify how it looks at T2. And this is my final configuration. and then I'm trying to find how the string looks like in between. Right? So this is just the initial data. And so it's reasonable to set delta psi at t1 equals to 0 and delta psi at t2 equal to 0, which of course causes this term to vanish. Right? So I'm just fixing how the string look like at t1 and how it looked like at t2. So finally, I have this term here, and that term is asking, well, what's happening with the endpoints of the string? What's happening at this end of the string at x equal to 0, and what's happening with that end of the string at x equal to a? Okay, so this is this is in time. This is fixed end. In space. So these are really how the fixed endpoints, well, how the endpoints of the string look like. So this is in space. It's also in time. And so what this really describes is the boundary data. So what this endpoint is doing and what that endpoint is doing. So we have to still kill this third term, right? So this is killed by imposing the Euler-Lagrange equation here, by imposing the wave equation. This is quite natural things to impose the initial data. The string look like this at this time and that time. But I have to also make this term equal to 0. And you have people typically consider two possibilities. So one possibility is the Dirichlet boundary condition, and the other one is the Neumann. So two possibilities. To make the term px delta psi 0 and 8 vanish, make vanish. So the first possibility is the Dirichlet condition. So in the Dirichlet condition, you say the endpoints are actually fixed. So delta psi at 0 equals to 0, delta psi at a equals to 0. So I really fix the endpoints. I keep the string really here fixed. That means also if you want that psi dot at 0 equals to 0 equals to psi dot at a. So that's one possibility. The other possibility is that I say, well, I let the endpoints actually freely move, but then this guy actually has to be 0. And that's called Neumann. So number 2 is Neumann. And that requires that px at 0 equals to 0 equals to px at a. But px is just psi x, derivative of psi with respect to x. So psi at x, psi x derivative. At 0 equals to psi x at a. And so that's the second condition. Doesn't matter which one you impose, certainly this term will vanish, right? So I have two possibilities. I can either fix the endpoints and let the string fluctuate in between, or actually I release the endpoints, they can do whatever, but then I have to prescribe that this is true at the endpoints. Okay, so now, of course, now we already study the string theory. The string theory is nothing else than studying strings like this, except the only difference is that the string is now relativistic. And you can show that for relativistic strings, these, well, so your string can vibrate in two different directions, and now I don't. So it can vibrate in the direction, in the longitudinal vibrations, and it can have the transverse vibrations. That's for the non-relativistic string. I think for the relativistic one, you have extra symmetry And so is it true that the longitudinal ones don't make any sense, and it's only the transverse vibrations which make sense? Probably true. So this is really like relativistic string. So everything goes exactly the same except it is relativistic, right? So things are slightly different, but everything goes the same. Again, you have to prescribe the boundary data, and you can choose. I choose the Dirichlet boundary condition, I get the Neumann boundary condition. So by choosing the Dirichlet conditions, I have to fix the endpoints. So now we have the string which is relativistic and moving in space-time, and it has to be fixed to something, right? So how do I fix the endpoints of the string? And that was the discovery of d-branes. So d-branes is basically the wall, which is fixing the string here, and it's fixing the string there. So now you have the d-branes, and so it took some time for people to realize that if you talk about string theory, you have to consider the possibility of Dirichlet boundary conditions. But if you have Dirichlet boundary conditions, you have to have an object which holds the string, and that must be a brane. So string theory is not a theory of strings only, but it also predicts the existence of d-branes and higher dimensional objects. And so in this case, if you want the Dirichlet conditions, you have the d-branes, and surprise, surprise, do you know where the d comes from? Dirichlet condition. So now you understand string theory. Okay? Let me stop here.